Good afternoon, everyone, and thank you for joining us to learn more about the CatCost tool. My name is Fred Badur, and I'm the PI of the project that developed CatCost. I'm going to begin by introducing some of the background of the project and describing what CatCost is, and then I'll hand it over to Kurt Van Allsburg, who is the lead developer on the project, and he'll go through an in-depth walkthrough of the tool. So the problem that we sought to address when we started this project was the high commercialization risk associated with biomass conversion technologies. Analysis work out of our laboratory has shown that in a number of biomass conversion technologies modeled, catalyst cost can constitute up to 10% of the total capital cost. In addition, the uncertainty surrounding the cost of potential breakthrough catalysts drives uncertainty in the minimum fuel selling price of the fuels produced during these processes. And to address this uncertainty and help mitigate risk, we have developed a spreadsheet and web-based catalyst cost estimation tool called CatCost that is easy to use and requires no outside process design experience. Our CatCost tool aims to enable researchers to build an understanding of economics of catalyst production and make more informed R&D decisions early in the catalyst development process. The release of CatCost in the fall of 2018 is the culmination of a 3-year collaborative effort between NREL and PNNO with the guidance of an industrial advisory board. Both the spreadsheet and web-based versions of the tool, complete with in-depth documentation and user tutorials, will be released in the fall of 2018. We built CatCost, integrating it with industry-standard estimation methods, and it's adaptable to a wide range of catalyst synthesis types and user experience levels. CatCost provides researchers with a number of ways to input their own cost data or built-in raw material libraries. Users are able to select from 2 modes of processing cost estimation, including a detailed full plant analysis or a simple step-based approach. Both methods are bundled with pre-populated templates to help users initiate an estimate for a wide variety of common catalysts, including metals on metal oxides, zeolites, and nanoparticles. In addition, CatCost captures the value remaining in discharged catalysts at the end of their usable life to understand the effective catalyst cost. And so we've effectively integrated some of the best industry standard methods into the cost estimation to make a powerful analysis tool. And so researchers are able to use CatCost to perform detailed sensitivity analyses, compare multiple catalysts and component cost analyses with our simple tool that has been verified with industrial market data. CatCost enables researchers to make better R&D decisions by providing them with actionable cost information and powerful interactive visualizations that make their cost analyses easy to understand. It has been built from the ground up with industry-verified analysis features, including the ability to scale any estimate to a desired production rate. Scenario and sensitivity analysis options allow researchers to test what-if scenarios rapidly and see what steps or materials contribute the greatest uncertainty. And researchers can also enter and manipulate data in any desired unit, removing the need for tedious conversions and allowing users to focus on the content of the estimate and not syntax. Coupled to the estimation capabilities of the tool is a suite of powerful visualizations that allow researchers to view and manipulate their data graphically for ease of analysis and presentation. We have designed the CatCost tool to be flexible for a variety of use cases to empower researchers to make better R&D decisions. And so as I mentioned, this will be free and will be released in the fall of 2018. You can get it at catcost.chemcatbio.org, where you'll be able to interact with the online web version of the tool, and you can download the spreadsheets and the documentation and some of the tutorial videos that we'll be putting out in the future. And if you have any questions from here on out, you can contact us at catcost@nrel.gov. And with that, I'm going to hand it over to Kurt Van Allsburg, who's going to give us a walkthrough of the system.
Okay, so let's start with the demo. And what I'm going to do here is take you through the process of completing a typical catalyst estimate using the CatCost tool, the Excel spreadsheet version. And the idea here is that you get a sense of both kind of our design philosophy and some of the estimation methods that are included in the tool. And I've completed a lot of the inputs already, but some I've left open so that you can see a little bit of the process. So for this, I'm going to do a platinum on titania catalyst. And so the first thing that I need to do is put in some broad overall inputs that go into the tool. And you can see that starting out in the CatCost Excel spreadsheet, that things are laid out in these tabs at the bottom in a sequence of steps that you need to complete in order to finish your estimate. We've tried to make it very easy to navigate and use. So we have to start here first at the Inputs tab, and I'm going to input some information like the catalyst name, And the basis year for cost estimation, so this is the basically when you're building the plant. So this uses built-in price escalation databases, both from chemical engineering and US Bureau of Labor Statistics. And then we want to select what units we're going to do our estimate in. So I'm going to select kilograms here. You can see that I have a lot of options. And all of these things are implemented in a way that makes it so unit conversions, price escalations, and so forth are all transparent and done for the user for your convenience, so that you can focus on the really interesting parts of the catalyst costing. So then over here, we have some inputs that basically size the production plant that we would be making this catalyst in. Of course, this is important because if we're trying to scale information from lab scale to industrial scale, we need to know what industrial scale means in this context. Now, as Fred mentioned, we have two approaches to processing cost in CatCost. One is a very sort of simple step-based method where you have an all-in cost, that's here in this first section, step method, an all-in cost for each step, like a filter, and that includes all utilities costs, operator costs, capital and operating, in a single hourly rate for that piece of equipment. This is based on contract manufacturer approaches to getting a price quote for manufacturing a catalyst at, say, a toller. The other approach is the Capex and OpEx factors approach. This is what you would be more likely to find in a traditional chemical engineering process design text. And this involves a list of equipment and operators costing every individual item of OpEx and Capex. So this is a little bit more detailed. And I'm going to show you both of those approaches. But you can see here that we have to enter some things for either of these approaches. If we were doing the step method, we would say that we want an order size of between 1 and 1,000 tons. And that determines some things like what size equipment at the catalyst manufacturer, since they already have existing sizes of equipment, what size of equipment would be used, and then determines some things like the length of this synthesis campaign and your selling margin. So you can see if I were to go for an order size of 200 tons, that the selling margin would be substantially lower. We actually have a just accepted paper on this in Organic Process Research and Development on that part. Then on the, again on the Capex and OpEx factors approach, where we're doing everything in detail, then you just have to enter some information like how big is this plant in terms of annual production of catalyst, how many operating hours do you expect, how much maintenance downtime will there be. So these are all things that are pretty standard in design reports like those published by our TEA group at NREL and elsewhere, and also by companies like IHS. So let's then proceed from these basic inputs to the next step, which is materials costs. In materials costs, I've already completed a number of these things, but what we're trying to do here is capture both sort of the stoichiometry and materials balance considerations and actually what materials are used in the synthesis. And so the first thing is to enter information about how large this, you kind of put in context the synthesis that you're entering. So if you're entering a particular consumption of materials, that has to be for a particular production rate of product. So in this case, the synthesis information that I've entered is to produce 1 kilogram of catalyst, so I'm going to enter that here. And you can see that some calculations are already done based on these inputs here. And we also have the option of using a percent yield calculation or to enter active phase mass instead, which might make more sense for a different application. We also assume something about some losses because inevitably when you're loading reactors and carrying materials around, you will lose some. So we've tried to capture little components like that. So down here, I've already completed how much I need of my metal source, but what I'm going to do is select that from our materials library. This is actually just a subset of the materials that we offer to users, but I wanted to make it reasonable to scroll through here. You can see that selecting a material and entering it in the list is really quite easy. You just select from the drop-down. And now that I have my metal precursor in here, the quantity and the units, I am getting a whole bunch of quantities calculated for me, notably the consumption in kilograms of this material per kilogram of finished catalyst, and the unit price, which is looked up from the library, and then ultimately the cost of that material per kilogram of finished catalyst. So what is its contribution to the final cost? Just to show you how easy this can be, I'm just going to add one more material here. I'm going to say, let's do hydrochloric acid, which is right here. And maybe I want to enter it in volume units, so I'll say I want to use 25. I can either type milliliters or I can look in here. And you can see that if the density is entered appropriately in the back end for this in the materials library, then it will automatically do all of these calculations to give me the amount of HCl that's required in kilograms, the units I selected earlier, and flow all the way through to a cost in the bottom line. Turns out HCl is quite cheap, even at this consumption rate. So that's our materials cost estimation component. And the idea is by the use of convenient unit conversions and stoichiometry calculations and the bundling of a materials library for which it's easy for users to add their own materials in their own library of common materials, including proprietary ones that you wouldn't find in our library. Through all of that, the user is able to accurately get materials costs for this component of catalyst cost. Now let's move on to the first method for doing processing cost estimation, and that is the step method. This again is the all-in approach where you have just a single hourly cost number for each particular step of a procedure, like a spray dryer or a ball mill. And what I'm going to do here is introduce a concept that it also applies for the other more detailed approach. And that concept is that what the user can do is either select from a list of pre-bundled process templates. So this is a pre-existing list of steps that we've developed for things like an FCC catalyst, a metal carbide, a PGM metal on carbon or metal oxide. For this one, I would choose the PGM on metal oxide, even though I'm going to look in more detail here. As you can see at the top, it says this is not included in the final estimate. I wanted to demonstrate the step method for you, but I think I'm actually going to look in more detail at the alternate approach. So you would not normally do both of these because then it would sort of be duplicating the same elements of cost. But one thing to note is that it is possible to combine these two approaches, the step method and the detailed Capex and OpEx factors method. The idea being that if you have this really detailed plant design and all these steps with operators and capital costs, operating costs, but then you want to change the process by adding just one additional step, it might be easier, rather than trying to figure out how to size that piece of equipment, just to use our built-in step method and add a single step. So that's the kind of use case that we would imagine that would be useful for. Now, as I mentioned, you can select from one of the process templates, or you can just enter a custom process. So in the custom process, oh, actually I have something entered here, but normally that would be blank. But you can see down here I have all these process templates. So I'm going to look at the one that we're actually using right now, which is metal PGM on metal oxide. And you can see that it has a number of process steps that are included, and these automatically scale to the correct order size that you've selected. And so basically the user could interact with this and modify these things, the power user could, or someone who's just looking for a quick estimate could just accept this information. They don't even have to look at those details. All they need to do is select from this drop down the metal PGM on metal oxide. So now let's switch to the more detailed approach, the Capex and OpEx factors approach, which covers sheets 3B through 3E here at the bottom. Again, this would be the alternate approach. You do not have to do both the step method and Capex and OpEx factors. So if we look at the equipment, we have the same choice essentially. We have a set of process templates, but the information included in these process templates is a little bit different. Now we're looking at a lot of detail. what is the piece of equipment, what material of construction is it made out of, how many, what size are we requesting, and of course the size units are different for each piece of equipment. So for a bin, for a feeder, it would just be a volume in cubic feet. For a pump or a compressor, it might be horsepower. For a tank, naturally, it would be volume. And a few things to note here. We have a very large list of pieces of equipment that we have available from various textbooks. This is, I think, the largest list of equipment cost correlations available anywhere that I'm aware of, at least in the open, in the public domain. So this allows you to select from a very wide range of high quality cost correlations. So what you do is, if you want to add a piece of equipment, it's going to automatically select the default material of construction, or you can override that. You can say whatever quantity you want, maybe you want 2 of those, and then the horsepower. I don't know what an appropriate horsepower is for this, so let's try 50. That's apparently too large. So this is giving you feedback here. One thing to note, these size limits here are giving you feedback on whether you maybe have chosen the right piece of equipment, but either way, even if you were outside the limits, or if you were inside the limits at the scale that you entered, but then as you chose a different industrial production scale and the CatCost tool automatically scaled it up or scaled it down for you, it incorporates logic to say that if you go above the upper limit of a cost correlation, it is going to automatically double or triple that piece of equipment until you're back in the correct range. Or if you go below the minimum size for a piece of equipment, it is going to automatically go to that minimum and price it at that, which is pretty standard chemical engineering process design practice. So these feedback mechanisms right here are really just to let you know that maybe you want to choose a different kind of compressor or something along those lines. So then let's scroll over here and see what it's doing with these inputs that the user has given. So the first thing is that CatCost is automatically going to scale the user inputs to the production scale in pounds per year, tons per year, whatever, that was entered on one inputs. So it will take the entered quantity and the entered size and scale it to an appropriate quantity and size at that design scale. And then, using the cost correlations that are built into the tool, it will develop a purchase cost and an installed cost for that piece of equipment, along with a labor factor. This labor factor is just the number of operators at any given time that are needed for that piece of equipment. So in this case where you see 0.1, that means one operator could split his or her time between 10 such pieces of equipment. If it were 1, that would mean that this piece of equipment needs a dedicated operator. And this information, stepping back, this information is then summed, and it is brought up. I haven't selected one yet. Since we're doing platinum on titania, I'm going to do wet impregnation of metal on metal oxide. But that information is then pulled from down there from whatever process template or the custom process you've selected, and is pulled up to here. And then that information will now flow through to the rest of the sheets. The next step after doing the equipment is your utilities consumption. Again, here we also have process templates. For each one of the equipment lists, we have a list of the utilities consumption associated with that process design, and this comes from Aspen modeling, so that the user, if they want to use a process template, doesn't have to do that. So again, the wet impregnation metal on metal oxide is selected already, and what that's pulling is the consumptions, and then we have unit costs, and ultimately that gets us to our utilities costs for this component of catalyst cost. Then the next part is where we get to the factors part of Capex and OpEx factors. Here what it's going to do is it will pull that total for the purchased equipment and the installed equipment from the equipment list, And it's going to then apply a number of fixed factors to get to other components of Capex and Opex costs. So purchased equipment here then is defined as 100%, but then we have factors for things like instrumentation and controls, piping, electrical, indirect components like engineering costs and legal expenses. These are all going into building the plant in the first place. And then analogously, we have the same type of factors for components of operating cost in the OPEX sheet. So most of this information is based on the direct labor cost. So it will round up the number of direct labor operators from the plant design, and then is going to add things for, say, laboratory charges, supervisory labor, overheads, and distribution, and so forth. All of these factors here are just fixed percentages. And one thing that I didn't highlight already that I'll just quickly show now is that for each of these values, we've built in scenario or sensitivity analysis to this tool, so that if I click up here at the top, there's this little plus icon. It's going to show that I not only have a base cost, so in this example, I'm estimating supervisory and clerical labor at 18% of direct labor up here. But I also have scenarios where I have a low scenario of 10% and a high scenario of 20%. So some of that information is built in, and of course the user can customize these numbers to maybe in-house values that they may have, or they can just accept them as is. The last component of the actual catalyst estimate that I want to show you is the spent catalyst part. Of course, in order to really accurately compare two different catalysts, it's essential to understand what's going to happen to each at the end of their life. If one of them is a PGM catalyst and the other is not, and we're not considering the value of that platinum metal content, then it's going to be a really grossly distorted comparison. So this section of the tool relies on some robust libraries that we have in the back end, thanks to our collaborators at PNNL and some consultants that have helped us with this. All the user has to do is complete a set of inputs here. I just deleted a few of these so I can show you the process of entering those, but we've already entered that we have platinum on titania, that the active phase is 100% platinum, and the bulk density, which I have a lookup tool for over here, so that if you aren't sure of what the bulk density of your catalyst might be, you can look it up. And then I'm going to select that we're using a fixed bed, which will affect how much attrition losses we expect for that catalyst. We do not have any contaminating metals from this list, and if we needed to landfill the catalyst, it would fall into the category of PGM or noble metal catalyst. So all of these inputs have then now generated a series of calculations of how much metal will we lose during the course of running this reactor with the catalyst in it, how much of the support will we lose, and thus how much total catalyst solids will we get after unloading the reactor to send to a refiner potentially. With that information, then we can calculate, based on the spot price for the metal. One thing I'll notice is very important that if you want to be using this in the future, that you're updating your spot prices, because of course that does vary a lot. It's going to calculate how much recoverable metal value there is there, and then based on information that we have that I believe has not been published in this form before, we also are able to estimate how much it's going to cost to do that recovery. So then you get a net recovery value, and this the tool is automatically going to choose the best option here, which we can see that the value of the metal at 104 is quite a bit higher than the fees at $6. So it's definitely going to be worth it to recover, and that's what we see down here. In a different situation, if I maybe selected aluminum, we would find that the best choice for this catalyst might just be to sell it, and then we will be selecting this sale value instead. Last thing to show is that we have sort of a range of complexities of outputs from the tool, starting with a very simple approach, which is just to show kind of a financial summary style description of all of these results. So if we were using the step method, we have a list of the step method outputs here, step costs and raw materials costs. You can see that raw materials costs are really dominating here, which is unsurprising considering that it's a platinum catalyst. I think, I should go back and change this from platinum to aluminum because that's distorting my results. Then down here for the Capex and OPEX factors outputs, this is designed to sort of just be directly comparable to something like you might find in an IHS PEP report, formerly SRI. So we have a breakdown of our capital investment, both broken down in terms of its annual depreciation cost and its cost per unit kilogram, per kilogram catalyst and so forth. And so the idea here is the user can do what they want with this information and they can drill down to greater detail. We have more detailed outputs also. I'm not going to go into more detail here because the last thing I want to do is show you the web tool that has been designed to mirror the functionality in this tool. And we even have, I should highlight, we even have, thanks to a really great intern working for us, we have the ability to interconvert between the libraries that are found in the Excel tool and the web tool. And the last thing I'll say about that is, even if you are using the web tool, all of that information is stored locally on your browser. So there's no risk, there's no disclosure of your proprietary information to us. The whole idea here is that you own your library, you can use our tool, we hope it's useful, but it would not be something where you have to worry about where your information might go. So we now are able to use these two tools very closely in tandem. So I'm now going to swipe over and see whether we can, it looks like this is working. So I'm just going to go to the home page here. I think I have too many things open on my computer. This is the web tool version of CatCost. And as I mentioned, it's designed to mirror what we see in Excel. In Excel, I didn't show you the actual materials libraries and equipment libraries. They were farther over in the sheets, list of sheets. But you can see that I have a materials library, an equipment library, I'm going too fast, and the spent catalyst library, all incorporated into this web tool. And that's what allows us to make estimates in here and have confidence that they will use the same calculation approach as in the Excel version. So I'll open this up and you can see that the same flow of information is here. We go from 1 inputs to 5 outputs. And you put in your basic inputs, materials costs, including adding materials to the list, add pieces of equipment, and we have the factors for capital and operating costs. One of the things that's great about the web tool is we have some really powerful and exciting visualizations like pie charts where you can zoom in on each individual component. You can click on materials and then zoom in to see what are my metal sources and supports and other materials, and then zoom in from there. And great tornado plots that are customizable on the fly. So it's a really powerful tool, and I think it goes a little bit beyond the capabilities that we have in Excel. Thank you very much for your attention, and it was my pleasure to present this really exciting tool and the work which has involved a really big team. We have, just at NREL, we have 4 or 5 people that have worked with us on the web tool. We have a great team at PNNL that has developed the spent catalyst component and the step method as well. In fact, all of that work was originated by a guy named John Super, who some of you may know, really knowledgeable, and has been a huge help to us in this project. So big shout out to John. It's been a very fun, exciting team effort, and we appreciate your interest and attention. We hope that when it is publicly released, and very soon, that you will use it, and hopefully it's useful to you, and that you will tell us what we could do to make it better. So thanks a lot.